Today we are going to do the last part of Brownian motion, which I am writing as Brownian motion 3. And today we are going to go do a very important part. So, we will be today talking about quadratic variation of a Brownian motion. What does it mean? Variation of this stochastic process, WT. W actually stands for Wiener, Norbert Wiener, who actually very formally studied the process in detail and made a lot of applications. So, a natural thing to do is that if you are given an interval 0 to t, there is no natural way to break the steps. Like for the symmetric case, symmetric random walk, you have a step every step 0, 1, 2, 3, 4. So, here you do not have any selected step length. So, what you do is take n very large and consider step lengths of the size t by n. And form the following sum. It is not so apparent what would be the limit if I take the limit of this quantity. So, if I take limit of this quantity as n tends to infinity, what is the idea? How to compute it? It is not so apparent, but the limit would be t. So, before really getting an idea of what it means, let us talk about the first variation and second variation of a continuously differentiable function. If you look at the sample path of a Brownian motion, then for a fixed omega, so once you fix an omega, it starts from 0. There is too much zigzagging basically, I am unable to draw, I am putting straight lines at some place. If you magnify them, there will be zigzagging. For every small zigzagging, there are further infinitely many zigzaggings. So, if you look at this, it essentially tells you that the curve is continuous as a function of t given a sample path omega. So, this for a sample path say omega, the curve is continuous in t, but is not differentiable at any point that you want. And so, second variation will take the value t, it will accumulate some second variation, while we will show that if you have a continuously differentiable function, second variation will always be 0. But let us just talk about what is first variation. So, if you take the interval 0 to t, the key point is to break it up into partitioning points, say n partitions. So, the nth partition will be given as points t0 equal to 0, t1, t2, tn equal to t, where you of course have tn equal to t. So, this is the basic partitioning of an interval that you do to compute the integral. So, if you write the first variation, So, you define some quantity of this form. And max of so for at the nth partition, this is what is called the maximum size of an interval, because these intervals need not be of equal size. One thing is very clear, that as you keep on increasing the number of points, this one will go down to 0, this will come down, as this is the maximum of all possible gaps, but if you put in more points, this value will come down, right. So, once you understand this, you can immediately conclude for the time being that as n tends to infinity, this is the first observation. Once you make this first observation, you see how simple it is to calculate the first variation. The first variation of a function over the time interval 0 to t of the function f, which is continuously differentiable. So, you will take a function f, say from R to R, does not matter, you can take Rn to R, we will just take R to R, because this W as a function of t is a function from R to R for each sample path. So, let us look at it. R to R or 0 t to R does not matter, if you are more comfortable, let us just put this is what. So, I am just bothered about this part, I am not bothered about the function's behavior elsewhere, because then I can simply write this as limit n tends to infinity, which is same as telling that norm pi n goes to 0. This one, now how do I look at it? Because once you have some information that this has a derivative and you want to have some information about the function, always use the mean value theorem. That is the biggest trick, simplest trick in analysis. So, what you are doing when you are taking the difference of this? So, by mean value theorem, there would be some xj star, okay, into tj plus 1 minus tj, where xj star is an element in the open interval tj plus 1 tj, not the closed interval. So, this is nothing but f dash x star j but if you look at it, this is nothing but a Riemann sum for the function mod fj and mod f, sorry. So, it is a Riemann sum for the function mod f, and this is nothing but the integral from 0 to t, sorry, not infinity, n minus 1. So, it is nothing but the integral, by very definition, it is the integral from 0 to t of mod f dash t dt. So, this is what is the meaning of first variation, which is pretty natural. So, let us come to the definition of the second variation. What is the meaning of the second variation of a function? Of course, you will do a little bit of jugglery, I am just removing this part. So, let us look at the second variation or the quadratic variation. So, quadratic variation is usually symbolized like this, and this is written as limit n tends to infinity. Limit n tends to infinity is same as writing norm of pi n tending to 0. Okay. The same thing, either you write that or you write that. So, as n goes to infinity, so j is equal to 0 to n minus 1. Instead of having the modulus the absolute value of the difference. So, what does the first variation do? It counts the total number of times the function goes up and down, up and down, up and down. That is what it is counting. It is counting the variation from here. So, if this is positive and this function value is say lesser than this, it goes down, and then possibly it can go up. So, it is counting the up and down, up, total up and down, the crossings. So, here I will write the same thing, but instead of looking at the variation in terms of the absolute value, I am doing in terms of the square, something like the mean square error type of thing that you must have heard if you have learned some statistics. So, this is summation. Now, I can here write the same thing. Like I have written x star j, where x star j is here. Maybe I will not write x star j, I will write say f of t star j whole square into tj plus 1 minus tj whole square. Okay. Now, if I write this as tj plus 1 into tj plus 1 minus tj into tj plus 1 minus tj, this breaks the square into two parts, the product of the two similar parts. Then one of them is obviously less than equal to this pi n, because pi n is the maximum of the interval size. So, I can write this thing of course as less than equal to limit n tends to infinity norm of pi n, because this is norm of pi n into summation j is equal to 1 to infinity. So, here again I have applied the mean value theorem. If you have not observed that, I have done the same thing, only instead of x star j I have put t star j. T star j is an element between tj, sorry I have a mistake here, it should be tj and tj plus 1, tj plus 1 is bigger than tj, please correct that, tj to tj plus 1. So, it is lying in the open interval tj and tj plus 1. So, basic mean value theorem, Lagrange mean value theorem basically. Now, you will write f dash, sorry here f dash. So, here please observe this f dash. So, you will have f dash of star j, t star j into tj plus 1 minus tj. Now, limit of this exists, limit of pi n, limit of norm pi n exists, this is 0, and limit of this also exists, because this is nothing but the integral of the mod square. So, what you will have? Of course, because I have taken f to be a continuously differentiable function, its square is also a continuously differentiable function, and hence it is integrable basically in the Newtonian sense and hence in the Riemann sense. So, this means this is nothing but limit of both of them exists, limit n tends to infinity. So, this is exactly equal to norm pi n So, here also I am writing limit n tends to infinity f dash t star j whole square tj plus 1 minus tj. So, this is limit, so this is nothing but limit of n tends to infinity norm pi n and norm big pi n, and this one is nothing but integral 0 to t f dash t whole square dt. So, this is a finite number because this is the integrable function. So, this is nothing but that has to be very, we want us to make sure that this is finite. So, because of our assumption this is finite, but so that this limit is going to 0. So, this whole limit goes to 0. So, what have we proved? We have proved the following, that for a continuously differentiable function f defined from on the interval 0 to t, it does not accumulate any quadratic variation. The square of the ups and downs, the total accumulation of the ups and downs, but the square of the values are added up, then that variation is 0. That is very, very interesting, because that does not happen with this one, but it does happen with this. But you will see immediately that the behavior of the, you can immediately understand also the behavior of the Brownian motion is so different, because it accumulates quadratic variation, while a smooth nice function does not accumulate any quadratic variation. So, how do I go about proving that the Brownian motion actually accommodates some quadratic variation? So, we will just prove this fact about the Brownian motion. So, the theorem W T is equal to T almost surely for t greater than equal to 0. Now, it is very important to note that this quadratic variation here is actually a random variable, because W itself is a random variable, it is a function, but it is a random variable. So, when you make these sort of variations, you are actually getting random variables. So, your convergence is in the almost surely sense, and that is we are going to show, and you will see a fantastic application of Borel-Cantelli lemma and a fantastic application of the Chebyshev's theorem, Chebyshev's lemma. That is what makes mathematics beautiful actually. So, when you deal with random stuff, always be sure that this guy would be always around you, almost surely this term, which means same as almost everywhere, this term would be always around you. So, let us try to prove this fact. This is known, this is very, very much a useful thing in finance. We will also at the end write down some shorthand which will be used in finance when we do the Ito calculus. So, again you do the same sort of partition the interval. Partitioning is something I am not going to write, because I have already written how I am partitioning the interval, what is your big pi n, what is the meaning of norm, the norm pi n is going to 0 as n goes to infinity. So, I am going to define a variation, total quadratic variation on a given partition, the nth partition, which as before would be from j is equal to 0 to n W T j plus 1 minus W T j. This is sometimes called the sampled quadratic variation. So, when you are talking about the sample quadratic variation, you have to observe that this q pi n is actually a random variable, because for this is a random variable, for I can put a particular scenario omega, and so you will have a q and omega that will give you a particular value of this for the same partition. Now, if you change the scenario omega to another omega 1, then for the same partition it will give you a different value. Now, what we are going to prove first is an amazing thing. Let me first tell you what we are going to prove. We will first going to prove that limit n tends to infinity, expected value of q n, q pi n, that value is t. Okay. This thing will allow us to prove that, and we will prove that limit n tends to infinity, the variance of q pi n is 0. Suppose I have proved this. Basically, what I am telling that if you average over all the possible paths, omega, then you essentially get the value of the quadratic variation. That is the meaning. If you take this and average over all the possible paths, then you get the value of the quadratic variation, which I claim to be t. Okay. Now, how do I actually say that this q pi n goes to t almost surely? And here you will see the use of Chebyshev's lemma. We will prove this later on if we have time. But let me, once I know this, how will I use this? The Chebyshev's lemma and the Borel-Cantelli lemma. Actually, I will use this idea. So now by Chebyshev's lemma, what will we have? And if we have this information, then by Chebyshev's lemma, we have this minus t, sorry, q pi n I should write, minus t bigger than n, this one is strictly less than 1 by n square variance of q pi n. So, variance of q pi n that been bounded, and that goes to 0 and hence it is bounded. I can still write this to be sorry, just do it 1 by n. So, this will become n square, that will be n square into c. So, what does this tell me? It tells me that limit n tends to infinity, probability of mod q n, sorry, q pi n minus t strictly bigger than 1 by n is less than or equal to 0, but probability is never a negative quantity. So, limit n tends to infinity bigger than 1 by n. So, it tells me that as n becomes very large, then the set of all omegas for which this is true is has measured 0, which says that q pi n converges to t in probability. So, if it converges to t in probability, does it converge to t almost surely? Let us look back at the literature. So, if we go back to our very old lectures on the Borel-Cantelli lemma section, then you can see that we have spoken about this. So, if xk converges to x almost surely, we have proved that it is q pi n goes to t in probability. Okay. Now, does it mean that q pi n will go to t almost surely? This is not a clear thing that it will go to q n will go to t almost surely, but that is what essentially you have to prove. So, we have come to this conclusion immediately by applying Chebyshev's lemma and this information. So, what we have that q pi n goes to t. Now, we can use some other techniques, some more involved techniques to actually show that q pi n also goes to t almost surely, which we will put up in the notes in your what is that called forum, because that will take too much of time to describe. So, just by applying the Chebyshev's lemma, by noting these notions, we have proved that it goes to Q1 converges to T in probability. So, what we have to show that Q1 converges to T almost surely. So, this is something which is quite involved, which we will not do in the lecture, but we will describe it in the class. So, hence we have come to the following conclusion, that this is equal to T, you are obviously sure that this is equal to T in probability, but this is equal to T also almost surely. That thing needs to be proved, that needs a little rewriting of this Q pi n and needs a little bit of tweeting the whole thing, so that we can apply Chebyshev's lemma and Borel-Cantelli lemma both to come to this conclusion. So, we will take a little bit of, it will be a little more complex thing. So, we will not do it now. So, what we have proved here, that if I can, this is easy to prove, this will take some time to prove, which will not again prove it. So, if you assume that this, if you agree to these two things, this is of course can be proved very easily, you can prove it yourself, and this is take time. Then by applying Chebyshev's lemma, you can at least prove that Q pi n converges to T in probability. But proving that it also converges to T almost surely needs the machinery, needs some more machinery, which we will not get into the class, but we will put it on the forum. Thank you very much.